in terms of work and what work really means in a realistic, how do we apply it sense. So if you're on, I believe we are at page 6 of our packet, we're going to want to look at thinking of work as being related to how energy is transferred either into or out of a system, since work is a transfer of energy based on the application of a force for a displacement. So since work is a scalar, that means that a positive work value indicates that the energy in the system has gotten larger, has increased. In other words, energy is added, hence the plus sign. Whereas if you get a negative value for work, it means that energy has been subtracted or removed from the system. This is very much a scalar quantity, so this is not so much left and right. It really is more and less. So let's take a look at an example where we've got a car moving that experiences a force to the left that was initially at rest at position x equals 0. And then at some time later, it's gotten up to a final velocity that is non-zero and is in a different position, but still experiencing the force to the left. So by applying a constant force in the same direction as the displacement, we would determine that the angle is 0 and therefore that the work is positive. And we can also say that according to Newton's second law, which is that F net is equal to m times the acceleration, or the sum of the forces, meaning forces forward minus forces backwards, we can use kinematics and the accelerations to figure out changes in velocity. So that means adding or having positive work increases the velocity and over this distance. And so doesn't that imply that work has to do with the change in motion of an object? And the answer is absolutely positively yes, it does. So reminder, kinetic energy is 1/2 mv squared and is the energy of motion. Then we can use that work is FD cosine theta. And for our case, we're just going to say let theta is equal to 0 degrees, meaning the force and displacement are parallel. So we can simplify it a second to saying work is equal to F times D. Now, using F net is equal to MA and the kinematics equation, V final squared is equal to V initial squared plus 2A times the quantity X final minus X initial, and replacing the quantity X final minus X initial with D, we can do a little rearranging to determine a value for A as V final squared minus V initial squared over 2D. Then we can plug in that value for A into the F net is equal to MA. So we'll get that F is equal to M times V final squared minus V initial squared over 2D. And we know that work is equal to the force, or m times the acceleration times the displacement. So working through that, we're going to find out that we can simplify this to work is equal to 1/2 mv final squared minus 1/2 mv initial squared, which leads us to the work kinetic energy theorem that states that the net work acting on something, keep in mind, net work means the sum of all of the works, is equal to the change in kinetic energy of the object. And please keep in mind that delta K, we're always going to do final kinetic energy minus initial kinetic energy. And so this is one of those times that if you're ever tempted to go back and go through those kinematics equations to try to find an answer, if you notice, you're going to end up with a ton more algebra. And so it's actually way easier to look at the net work is equal to the change in kinetic energy and the work kinetic energy theorem. And I am going to be insisting that in this unit, to receive full credit, you will need to use the energy approach. Now, for those of you who are wondering, no, you never have to show the full details of all of this, but I wanted you to see where this came from.